The hardware driving the current artificial intelligence boom exists at a scale that is difficult to visualize. NVIDIA's Blackwell processor packs 208 billion transistors onto a piece of silicon smaller than a postage stamp. Its successor, Rubin, increases that count to 336 billion. While the tech giants designing these components are worth trillions, they do not possess the facilities to manufacture them. To turn these designs into physical hardware, they must outsource the work to specialized third-party foundries. Mapping the global supply chain reveals a precarious structural reality. Companies like NVIDIA, Google, and AMD rely on foundries like TSMC and Intel, but those massive foundries all funnel down to exactly one point. They are entirely dependent on a single company to build the tools that print the chips, ASML. This Dutch firm holds a 100% monopoly on extreme ultraviolet, or EUV, lithography. The engineering involved is so complex that every major competitor eventually abandoned the market, leaving ASML as the sole provider for the entire planet. This means the pace of the global artificial intelligence expansion is effectively determined by the production capacity of one factory in the Netherlands. The journey starts with ordinary silicon dioxide, commonly known as beach sand. It undergoes a series of purification steps until it reaches 9 nines purity, 99.9999999% pure silicon, or fewer than one stray atom of contamination per billion. Using the Czochralski method, this hyper-pure silicon is melted at over 1400 degrees Celsius. A tiny seed crystal is dipped into the melt and slowly drawn upward while rotating. Atom by atom, a single continuous crystal grows into a solid cylindrical ingot over a meter long. Diamond wire saws slice the ingot into wafers less than a millimeter thick. These are then polished until they are flatter than almost any other man-made object, resulting in the shiny 300-millimeter discs that serve as the foundation for every chip. These wafers are the canvas for the transistor, which functions as a microscopic electronic faucet. By applying a voltage, engineers can open or close a channel to control the flow of electricity, creating the ones and zeros that drive all digital logic. To visualize the scale of these features, consider biological benchmarks. A typical virus is 100 nanometers across. A strand of human DNA is 2.5 nanometers wide. Modern transistors are manufactured with features in the single-digit nanometer range, smaller than a single molecule of DNA. An AI chip's processing power is a result of this density. The goal of the entire manufacturing process is to successfully pattern hundreds of billions of these microscopic switches onto that single piece of silicon. Carving those features requires photolithography, essentially photography at the atomic scale. According to the Rayleigh criterion, a mathematical rule of physics, printing smaller features requires a shorter wavelength of light. To move past the limits of deep ultraviolet light, ASML spent 3 decades and $9 billion to develop extreme ultraviolet, or EUV, lithography. This technology utilizes a wavelength of exactly 13.5 nanometers. Because there is no simple bulb that emits 13.5 nanometer light, the machine generates it through a violent physical reaction. A generator fires 50,000 droplets of molten tin per second, and a high-power laser strikes each one, flattening and exploding it into a plasma. This plasma reaches 200,000 degrees Celsius, many times hotter than the surface of the sun. The process must occur within a vacuum, because air is dense enough to absorb EUV light before it can reach the wafer. Since EUV light is absorbed by glass, traditional lenses are useless. Instead, the beam is steered by mirrors made of dozens of alternating layers of molybdenum and silicon, designed so that the reflections from each layer add up to bounce the light rather than absorbing it. These mirrors are among the flattest objects ever made. If you scaled one of these optics to the size of Germany, the tallest bump on its surface would be only 1/10 of a millimeter high. ASML's monopoly is maintained by its ability to take these extreme physical phenomena and integrate them into a reliable mass manufacturing tool that can operate 24 hours a day inside a chip factory. Scaling continues with a new generation of machines called high-NA EUV. These use larger mirrors to capture light at steeper angles, allowing for even finer resolution. A single high-NA machine weighs over 150 tons and costs roughly $400 million. Shipping one requires 13 cargo flights to move the components to the customer site. The cost of these machines ripples through the supply chain. Running a wafer through the dozens of EUV layers required for a 3-nanometer chip pushes the manufacturing cost of a single silicon disk toward $20,000. To manage these costs, manufacturers are moving away from single, massive chips. They now use advanced packaging to stitch smaller, high-yield pieces together, ensuring that a single defect doesn't ruin an incredibly expensive component. As the industry pushes toward the limits of physics, the barrier is increasingly becoming financial. The continued progress of Moore's law now depends on whether the market can generate enough profit to justify the escalating price of the tools needed to build the next generation. The development of EUV was so expensive and risky that ASML's primary customers, Intel, Samsung, and TSMC, had to directly buy stakes in the company in 2012 to keep the research program alive. That collective investment resulted in a singular choke point. Because ASML is the only source for this technology, its lithography machines have become instruments of geopolitical power. Under export controls coordinated by the US and the Netherlands, ASML is legally prohibited from selling its EUV systems to China. Controlling the hardware that makes the chips has proven to be a more effective way to limit a nation's AI capabilities than trying to control the software or the final chips themselves. Every response from a modern AI model is the result of this improbable engineering. It is made possible by a droplet of tin, vaporized in a vacuum, inside an impossible machine built by a single company in the Netherlands.